Good evening and welcome to the live sessions for the NPTEL course on Fundamentals of Additive Manufacturing Technologies. It is 6 p.m., but participants are here to join. So we will wait for a few more minutes before we get started. Thank you.
I got started with implementing the spot melting simulations. For laser on time, I thought we can get an approximation from the time that a point spends inside above liquidus from something like Rosenthal analysis, and maybe we can also add some preheat temperature just to simulate the heat already present because of the approaching source. So I've started setting it up once I have results.
Good evening and welcome to week 11 of the live sessions for the NPTEL course on Fundamentals of Additive Manufacturing Technologies. This course is taught by Professor Sajan Kapil, who is a member of the faculty in the Department of Mechanical Engineering at IIT Guwahati, and I am Sourav Goswami. I am a PhD candidate in the Department of Mechanical Engineering at IIT Bombay. During the course of this session, we have looked at several additive manufacturing technologies, and now we are say near the conclusion of this course. In fact, this being the penultimate week, and We have been following categorization of the process based on the feedstock morphology or feedstock type, and we have already dealt with liquid feedstock based AM processes, sheet feedstock based AM processes, then wire based AM process, and we are currently dealing with powder based AM processes. Uh, Last week we already looked at the blown powder type processes such as direct energy deposition using blown powder, in which case the powder is delivered to the desired region on the substrate or pre-built layer by some carrier gases. Here today we'll be discussing different type of process, still using powder as the feedstock, but this time uh, the powder feedstock is available in the form of a bed, of which uh, a specific quantity of powder will be spread in the form of a thin layer over the printing region, and we'll be curing, sintering, or melting some part of it using certain processes. And such processes are typically called powder bed based on processes such as liquid powder bed fusion, selective laser melting, selective laser sintering, and so on, as we'll encounter shortly. Also, in between, we had a bonus extra session where we discussed the fundamentals of numerical modeling of additive manufacturing. Of course, the motivation arising from the fact that AM is inherently say capital intensive manufacturing process, whether it is in terms of purchasing and commissioning the machine, which itself will cost a very healthy sum for metal AM, metal 3D printers. The feedstock is also very expensive, especially say if it is powder feedstock or some exotic alloy, and it also requires expertise for handling and printing production parts. They will be free of defects. And so, when we are trying to optimize the additive process for a new machine, a new material, or we are trying to develop a new technology, or say use a new laser of different wavelength or different power distribution instead of the usual Gaussian or uniform density, a power density, then rather than doing many trials and errors using the experimental setup, which will cost a lot of money, it will be much more convenient if we can come up with a reliable model which can say very effectively and very faithfully recreate the experimental conditions in our computer itself. And once we have a reliably working model that can say represent or capture some specific physics, uh, it's then only a matter of changing the parameters to obtain new results and test for various parametric cases. Of course, it is very difficult to have a single model which can capture all the physics or address all concerns related to the additive process. Uh, for instance, only thermal models or heat conduction based models of the additive process or welding are very frequently encountered, and they are typically leveraged to predict residual stresses and distortions in parts, or to check for melt pool geometries, bead width, bead depth, and bead size. But they may not be able to very faithfully recreate fluid flows inside the molten pool. Or say if you're focused more on the micro scale, then something like dendritic features or microstructural features. Similarly, however, they are suitable for even part scale, or at least for tens of mm. On the other hand, if you are working with something like a phase field model or a very highly reliable fluid flow model, it will be able to recreate heat transfer and flow currents inside the melt pool. Based on the resolution we are looking at, it may also be able to say predict uh, segregation profiles or dendritic features such as primary and secondary dendrite arm spacing. But then it will only be limited to very small domains and will not really be applicable at part scale, because the calculations will simply become untractable despite the use of say state-of-the-art computing facilities. And so there is a need for multi-scale model of AM processes. Uh, we also looked at the ways in which energy addition to the system is simulated, say typically by the use of an energy source, which may be of volumetric or surface kind, how they're implemented, how heat losses such as due to convection and radiation are modeled. We also saw how we can just use a single effective heat transfer coefficient to model the effect of both, and what effect nonlinear material properties will have on the solution. Uh, Today we'll be discussing about powder bed-based AM processes, starting with a little history on this process, then the typical machine architecture, classification of processes, then selective laser sintering and direct and indirect sintering processes. Of course, the name sintering would imply that here the temperatures that we'll be dealing with will typically not exceed the melting point. Uh, in fact, we'll see that they range somewhere from 50% of the melting point till the limiting value of the melting point itself. But it's still a sintering process. It's not a fusion like melting and solidification process. And as we already looked before, the powder additive manufacturing can be classified into a powder feed type and a powder bed type additive manufacturing process. In a powder feed process, the deposition head has nozzles, and we saw a good number of various configurations in which either the laser comes from the center and the powders come from the side or the other way around. And this powder is delivered to the substrate or pre-deposited layer by the use of some carrier gases, which also serve other functions, such as shielding the melt pool from the atmospheric gases such as oxygen, uh, say acting as a protective blanket for the laser optics, but primarily to deliver the powder particles to the substrate. Now, because they are carried by the carrier gases, we also saw that typical numbers for particle velocity can be of the order of meter per second and can reach values of 5 meter per second very easily. Because of which, not only is mass being added to the system, but also momentum that these particles bring and energy, because these particles will interact with the laser beam during their time of flight. And depending on their trajectory and the time of interaction with the laser, they may melt fully or partially. So they'll also be stripping off a fraction of the laser energy and delivering it to the substrate. What we also saw is the efficiency or mass deposition efficiency in this case is limited by certain considerations, primarily because of the very high momentum that these particles bring and that they can bounce off, so there can be powder spatter. Then there is the catchment efficiency, which is the mass of powder particles that actually goes into building the bead over the total mass of powder which was fed to the system. And we see that often this catchment efficiency will be in the 30 to 40% range. Of course, it will depend on the configuration, and even the spatter is significant. Uh, this process has good deposition rates, but because of the higher, uh, say, layer thicknesses, often the resolution will be not as good as the powder bed type processes, where we have a reservoir of powder out of which a specified layer or pre-chosen layer of powder will be spread onto this printing region in the form of a powder layer using something like a doctor's blade or a roller. And this very thin layer of powder will typically have, say, thicknesses of the order of tens of micron, so some 40 to 50 micron maybe. And once this layer is printed, the bed will go down and the next layer of powder can come sit on top. Clearly, we see that here the powder particles do not really have any, say, inertia of motion associated with them. Whereas in the previous case, the powders were reaching the system with certain momentum. Uh, the powders only have motion at the start of the layer, where while they're still being shifted into the printing region and be compacted into a single layer. But after that, it's just the laser which is scanned onto the print region and suitably reflected or moved around using galvanometers that interacts with the powder particles, and then depending on the process either centers or melts them in region. And so in this case we do not really have any efficiency terms analogous to, say, the catchment efficiency of powder DED process. However, what we can clearly say is that in terms of powder economy, this process is less efficient unless we are printing a large number of parts on the bed at a single time. If we are just printing, say, a single part, we will still need to fill the entire bed or the entire printing region with powder. And even though we are centering only this small region, the rest of the powder uh, does tend to get affected and their properties change because of the localized heating and cooling and fusion. And they may also pick up some contaminants because of interaction uh, with the atmosphere. And so typically this powder is not readily recyclable. Of course, for very highly controlled processes, most of it may still be, we may be able to recycle it, but typically it will not be recyclable. So unless we are printing, say, a full bed full of parts using the powders, a lot of it will end up getting wasted. Now, the powder bed processes themselves can be classified into either binder-based powder bed additive manufacturing, in which case we have this jetting head, which can selectively dispense droplets of binder onto the required region, and then the binder can uh, say bind together the build powder and can form hard parts. Of course, it might require some pre post processing like a sintering step in order to achieve final product level hardness. But still, this binder will achieve some minimum level of or impart some minimum level of strength to the part so that we are able to handle it. And of course, a classic example which Professor Kapil gave during his lecture was that of water and cement or concrete particles, where cement is the built material or the structural material, and water is the binder, which imparts strength to the cement particles. The other class of powder bed based AM processes is of energy beam based powder bed additive manufacturing, which can again be divided into two based on the type of energy beam being used. We can either work with a laser based laser beam or we can work with an electron beam. Electron beam based processes are typically called electron beam melting or EBM. So and powder based processes are classified into selective laser sintering and selective laser melting. Of course, the distinction between the two being that in one case, the principle or the principle of fusing these materials together is just sintering itself, whereas in the other case it is melting and solidification. And so the temperatures which will be achieved in these processes will be lower for the sintering case. And just a second. Yeah. So the present slide contains a timeline of the development of selective laser melting type technologies. It was in the 1970s that P. Sirod proposed the application of powder laser process for object manufacturing, and later in mid 80s, when Householder gave the description of a process which was very similar to selective laser sintering. So basically laying the foundation for SLS and SLM. Also, his contemporary C. Hull proposed a detailed working method and apparatus for building objects layer by layer, which we today know as the classic definition of additive manufacturing. In late 80s, Deckard uh, showed the first working prototype or commercial machine of a selective laser sintering process. Later, Fagan produced a machine for powder-based process similar to SLS, but not quite the same. And it was also around this time that the famous 3D printing company called 3D Systems Corporation was founded. And very soon others sprouted, such as DTM Core, EOS GmbH, which is still one of the most well-known powder bed fusion manufacturers. In fact, typically, if you have, say, uh, a facility for making patient implants, which actually go into the body of a patient, there's a very high chance that it will be printed using an EOS machine because of how highly standardized they have come to be. Then there were others such as FNS GmbH, Arcam, which is a Swedish company, and these days it is most well known for making electron beam melting machines. Even though, as per this diagram, the very principle of electron beam melting was proposed much later. So I guess at this time Arcam might have been involved in some other form of R&D or inventing some other technology. A Chinese company, Beijing Yinhua, and then Concept Lasers GmbH. It was also around late 90s when R. Larson proposed the principle or a working concept of electron beam melting. And later, at the turn of the century, miners Wissenbach and Gasser showed the lasers or developed the selective laser melting technology. And also around this time, DTM Corp merged with 3D Systems, and around 2000s, MTT Technological Groups was founded. So here we have a schematic diagram of the powder bed based EM processes, and just like our other or our previous sessions, uh, it features a subsystem based classification based on the joining mechanism, the powder material, the scanning system, the powder delivery system, powder recoating system, the build atmosphere, and the build platform. So details of each are we'll be visiting in the subsequent slide. But let us take a moment to look at the schematic of the machine itself. So on the left here, we have a reservoir of powder, and depending on the chosen layer height, there will be an upward motion uh, to push out the required or estimated calculated quantity of powder up, which will then be transferred onto the printing region by this recoater. The recoater may be available either in the form of a doctor's blade, such as shown in the figure, or it may also be available in the form of a roller. The purpose of the recoater is to again transfer this powder from the reservoir onto the printing region and spread it out evenly as per the desired layer thickness. We see a substrate plate here, which is bolted to this printing bed and which moves down. So for each pass, the stage will move down as per the desired layer thickness and allow for the new layer of powder to come in. We have a laser beam which is being deflected all over the printing region by this mirror or galvanometer. And we also have a blow up of an example part being printed where the part has support structures as well as it is surrounded by unsintered or unmelted powder. Now, typically in such a powder bed based EM process, the surrounding particle or the surrounding powder particles, if well compacted, may themselves act as support structures. And so, additional support structures may not be always required depending on the machine and the material and the geometry. Then support structures in this case serve an additional purpose, which is to not just prevent any overhanging features from falling down. So say I am printing something like this part. Because of overhang, this region will tend to fall down, and so I will want to have supports in this region. In the absence of support, this part will simply collapse. In this case, however, uh, the surrounding unmelted or unsintered powder particles can maybe assist in taking the weight of this unsupported region. But what we are more worried about is also because of warpage, what if it moves up? Because then in the next pass of the helicopter blade, these two may collide. And that will end up damaging the machine, stopping the print, and send the machine into downtime. Not to mention that involve a lot of cost. And let us look into each of these aspects in more details in upcoming slides. So for the case of powder bed based AM processes, the joining mechanism can either be sintering, it can be melting, or it can be a sort of hybrid of the two, something called liquid phase sintering. The process of sintering applies enough heat to bond the particles, but not enough heat for the particles to reach melting point. Typically here, the temperatures are between half of melting point to just the melting point, but not exceeding it. And here, the powder particles will tend to fuse by atomic diffusion, which leads to this formation of neck. Eventually, the powder particles may take on an appearance like this. However, there are other considerations in place, such as coarsening, in which case a large particle will continue to grow larger, while a small particle will just end up getting, eroded. But this is the basic principle. On the other hand, and the reason we are applying heat for the sintering process is to enhance this diffusion process. Uh, on the other hand, melting up sufficient heat to heat the powder particle above the melting point or liquidus point of the alloy, causing the powders to become liquid. And once, say, all these powders have become liquid, uh, mixing and diffusion in liquid state is far more potent. So all of the powder particles in the molten state will mix, and once the heat source moves away, they will again solidify to form a part. The middle road, which is liquid phase sintering, is a sintering technique which uses a liquid phase to accelerate the interparticle bonding of the solid phase. High diffusion rates are associated with liquids, giving fast sintering or lower sintering temperatures. And so, because of the lower sintering temperatures, this may especially be useful, say, if you are working with a low laser power setup, because typically in powder bed fusion, the laser powers rarely exceed 500 volts. Or if you're working with, say, something like a refractory metal, which has a very high melting point, in which case, anyway, even with very high power lasers, it may be difficult to achieve the melting temperature or a superheat temperature. Or if you're working with, say, very reflective metals, such as copper and aluminum, which also have high thermal diffusibilities, and melting them locally itself becomes a challenge because of how fast they diffuse away the heat. It involves sintering under conditions where solid grains coexist with a wetting liquid. And two types of powder mixtures are possible here. One is the case of mixed powders, where we have a high melting temperature component and a low melting temperature component. the higher one providing strength, whereas the lower one provides the matrix to bond these particles. And we can have pre-alloyed powders in a process also known as super solidus liquid phase sintering. Now, for this sintering process, the type of powder material may be coated, mixed, pre-alloyed, or it may be a polymer or wax powder or a metal powder. Depending on the type of powder used, the processes are classified as indirect or direct route of sintering. In indirect route, the laser beam does not melt or sinter the powder particle of the desirable material or the structural material. Rather, a sacrificial binding material is first used to melt by the laser power and hold these powder particles together to make a green part. The final product is produced by post-processing of the green part in a furnace, where the sacrificial material will typically be burnt off and vaporized. In the case of direct route, the laser beam sinters or melts the structural material itself onto the powder bed, and very minimal or no post-processing is required. Typically for metals, the post-processing which takes place is called hot isostatic processing or HIP, which serves to reduce the porosity and increase the density of the final parts. And here we also have a helpful schematic of the types of powder that may be used. So we may have coated powders where the structural material is shown in blue and the coating is shown in green. Uh, when the laser interacts with these particles, it may just melt this low temperature coating, while the high temperature structural powder remains unmelted or only partially melted. The melting of the coating will provide the necessary liquid matrix that will allow these particles to bond together. And once it solidifies, they will be held in place. Or we can have mixed powders, where instead of the low temperature component being coated individually onto particles, which will be a costly and sophisticated process, we can just physically mix them together, trying to achieve a good uniform distribution. Of course, it might be difficult because what can end up happening is if they have large powders or particles in one region, all the say binding material or low temperature components segregated into a separate region, in which case this process will be defect bound. Or we can have partially pre-alloyed powders, alloying of course being a chemical change, in which case some of these low temperature components will be alloyed onto the metal particles, or we can have a fully pre-alloyed powder in which they are absorbed into the chemistry of the alloy itself and can be later liberated during the sintering process. Next, to discuss the working principle for the indirect route of sintering, where the coated powder are preferred for individuals. The coating can be of any material that exhibits lower viscosity upon heating. Thermoplastics are known to typically satisfy this requirement, and further, they can also be repeatedly heated to soften or melt, and they can be cooled to solidify as the temperature passes through the glass transition temperature and the melting temperature T. When ceramic or metal parts are desired, thermoplastic polymers are used as fugitive binders in the powders. The idea, of course, being to have a low melting point material adjacent to the powder substrate so that the latter is more easily compacted to produce green parts. Subsequent to green part formation, the binder is either chemically converted to a higher melting point substance, or more typically, it will be thermally decomposed and eliminated. The part created at this stage is called the green part. When the binder elimination occurs, the part is kept in a furnace at certain temperature for certain amount of time. Hence, the binding material is simply burnt away. The parts at this stage are called brown parts. In the second stage of post-processing, the brown part is further reheated while in direct contact with an infiltrate material. In this case, the infiltrate material will flow by capillary action into the pores of the brown part to create the fully dense product. An example of infiltrate material and build material can be stainless steel and copper, where steel is the build material and copper is the infiltrate material. In contrast to conventional sintering, however, no compaction pressure is applied in indirect SLS. As a result, while the green parts are of lower density, they are nearly isotropic and free from any residual stresses. So it is somewhat analogous to the pressureless sintering phenomenon. The low density can of course be a cause of concern because if the part density is too low, it can distort during post-processing in a furnace or even get damaged during cleaning and subsequent handling. Thus, it is desirable to have a green part density of at least 50% and a strength larger than 1.7 megapascals. The key advantage of SLS is that it is capable of yielding functional parts in essentially final materials. It is possible to produce parts considerably stronger than those produced by SLA. No support mechanisms, and further, the process is very simple because there are no milling or masking steps required. The uncured material is easily removed after build by brushing or blowing it off. However, this also produces a lot of wastage. The coated powders can be very expensive and also bring issues associated with non-uniform coating of the powder particles. Another possibility for indirect sintering is by physically mixing the high melting point particles with the low melting point particles. Usually, the low melting point particles are of smaller size, and this results in high packing densities. This packing density can also be improved by something like vibration of the bed. However, in this approach, sometimes the powder particles get segregated while the decoding plate moves over the bed. And here we have an example of such a process where rather than using coated powders, which as you can see can sometimes result uh, in interparticle porosity, here they are just mixed together and we see that porosities are largely eliminated as well as lowering the cost of the powder because powder coating can be pretty expensive. Now in these processes, the polymers are processed directly without using binders because they are very low melting temperature phases. However, in the early stage, to produce the parts by direct route, the mixed or pre-alloyed metal particles are used. And this is mainly because of the balling defect due to the availability of low power lasers. Uh, because at the outset, the reason that selective laser melting took, say, a couple of decades to emerge from the selective laser sintering process is because laser technology had not kept up. Originally, we had CO2 lasers, which are typically of a higher wavelength, like 10 micrometers, and also are not very powerful. Secondly, also we saw that laser material interaction is often controlled by the laser wavelength, and certain materials will interact better with specific wavelengths, such as copper will be more amenable to say smaller wavelengths like green or blue lasers, whereas ferrous alloys such as steel or nickel superalloys such as Inconel or even titanium alloys are yeah, easily amenable to infrared lasers, typically of the wavelength of 1 micrometer or so. And it was only with the advent of more advanced lasers that these particles could be melted because for say a CO2 laser of 10 micrometer wavelength, even if you run it at very high power, there is a good chance that the material will not interact sufficiently and will still not melt despite the very high powers involved. That is why in the early stages, uh, mixed or pre-alloyed metal particles were still being used. And due to low laser power, the sintering necks are formed within a limited liquid amount region. The molten material in the focus spot area of each point tends to aggregate into a single coarsening sphere whose diameter is approximately the diameter of the laser beam, leading to the Bolling effect. And here it is also illustrated. So we have, say, approximated the motion of the laser at two discrete time steps by these two laser spots. And in one case, we see how these two liquid spots do not interact sufficiently. There is limited liquid formation and the occurrence of balling defects, which is also illustrated here, where we can clearly see a lack of fusion between these two adjacent balls. Whereas in the other case, if they interact sufficiently and centering necks are formed as a consequence of sufficient liquid formation, then we have a continuous track. And here the centering neck has formed. It was later realized that the balling effect can be reduced by using a two-phase metal powder, and this led to the use of mixed or pre-alloyed powders. They also enabled direct selective laser sintering, and the first direct metal laser sintering or DMLS machine was developed by Electro Optics EOS of Munich, Germany. EOS INT M250RP, a popular EOS machine, uses a 200-watt infrared laser with a spot size of approximately 300 micrometer and pre-alloyed powders that yield a laser cure width of about 600 micrometers at a scan speed of 3 meter per second at the standardized layer thicknesses of 50 micrometer. So 3 meter per second is sufficiently high speed, as you can imagine. Mixed powder technology, on the other hand, is found to be applicable in the direct SLS of several mixture powders. The material to be sintered comprises a structural powder or the structural material with relatively high melting point and a binder powder of low melting point. Uh, the reason being to enable liquid phase sintering. Sometimes a flexing or wetting agent may also be used to improve the wetting characteristics. And we have a few examples for metals, such as in the case of nickel and tin. Nickel melts at 1455 degrees Celsius, whereas tin melts at 232 degrees Celsius. And the resulting compound can be composed of Na2SN, Na3SN2, or Na2SN4. The nature of LPS will clearly depend upon the characteristics of the powder blend and the sintering process itself. More recently, however, the idea of full melting of metal powders has been explored, supported by the continuously improving process parameters in terms of smaller layer thicknesses, smaller spot sizes, uh, which result in mechanical properties being much better than earlier time selective laser sintered parts and compared almost with wrought or bulk metal properties. Now, in terms of the scanning system, we can either use a galvanometer with passive and active optics. As we would recall, galvanometer is just a pair of mirrors which are mounted onto motors and which can move very quickly based on their angular deflection. They can deflect the laser spot all over the printing region at very high speeds because of the small inertia of the mirrors. Or we can have flying optics because when deflecting the laser spot uh, far away from the incident axis, there will be, say, defocusing, as in 3D space. The locus of the focal spot will be in the form of a sphere. This can, of course, be corrected by the use of f theta lenses. Also, when we are deflecting far away from the optical axis, the beam shape and the energy distribution will change because far away from the axis, the will no longer continue to have a circular cross section. Rather, it will become elliptical. And so we have seen that in few machines, flying optics have been installed to take care of these effects. Of course, on the other hand, flying optics are expected to have lower scan speeds than galvanometer based systems because lasers generally consist of very sophisticated and very costly optical systems which cannot be just moved around at very high speeds because it risks damaging them. Or the scanning system may also consist of something like a mask and flood lighting. However, I'm not aware of any commercial systems that use such a process. The powder delivery system itself can either be top feeding, as shown on the right here, or it can be a case of bottom feeding, as shown on this side. In the case of top feeding, we have these powder hoppers which dispense powder from the top onto the print region, which can then be spread out using something like a reporter blade or a roller. Whereas in the case of bottom feeding, the powder is available from this reservoir, which raises each time to deliver a specified or pre-calculated quantity of powder ahead of the recoater blade. And the recoater blade then transfers this powder onto the printing region, spreading it out into a single uniform compact layer of desirable thickness. Now, the recoating system itself may either be like a doctor's blade, or it can be in the form of a roller, or it can be in the form of a slot feeder, or there may also be some electrostatic type recoating systems. The blade type system, such as shown here, again will just consist of, say, a strip of metal uh, which delivers powder ahead of it and is expected to produce a flat layer of powder. Typically, this doctor blade like recoating system tends to have or can handle higher quantity of powder. Per layer. However, the layer that is generated may not be as uniform or as compacted as the ones achieved by powder recoating system using a roller. And the reason for this is because of the degrees of freedom available. So in the case of blade, we only have 1 degree of freedom, which is, say, just the translation. Whereas in the case of ruler, we have 2 degrees of freedom. We have translation as well as indicated here, we also have the rotation of the ruler. And so rollers typically tend to produce uh, better compaction or more uniform layers. And again, based on the type of motion, they can have different effects, which we'll discuss in the upcoming slides. We can also have slot feeder, where, as we can see, this funnel-like feeder, which contains the powder particles, just moves over the region and delivers powder under the action of gravity. Or we can have an electrostatic type recoating system, where the build substrate itself is mounted onto a rotating hinge, uh, which can rotate away from under the laser. Then it can have a temporary electrostatic field, which will uh, say in this case it is the bed is positively charged, whereas the reservoir is negatively charged. And so there's an electrostatic force of attraction between the substrate and the powder particles inside the reservoir. They will get attracted and they will stick onto this build substrate. Of course, say the thickness of the layer and the uniformity and the packing fraction will have to be, or the packing density will have to be adequately optimized It may not really be so easy to control all of these parameters independently. But once we have been assured that, say, a reasonably good powder layer has been formed, then it will swing back into place and then the laser can scan this. Now, we can have either a counterclockwise rotation uh, with respect to the traverse direction, or we can have a clockwise rotation with respect to the traverse direction. Here, the traverse direction is reverse, whereas the overall sense of rotation of the ruler remains the same. Uh, when there is a counter rotation of the ruler with respect to the transverse direction, we can expect that, say, any particle which is available right ahead of it is being pushed upwards, and this leads to better flowability of the powder particles. Whereas in this other case, uh, where the ruler has a forward rotation with respect to the traverse direction, the powder particles which are available just ahead of it can be expected to be pushed under it, and so there will be better compaction for the forward rotation case. Of course, uh, another strategy which can be used is to have both of these motions, as in the roller still continues to rotate in the same direction. In the forward pass, it improves the flowability of the bed, and then it rolls back or does another pass where it compacts the bed for good packing fraction. There may also be some other hybrid methods, such as a vibrating counter rotation of the roller, which, as you previously saw, may or has been shown to improve the packing density of the powder bed. In conjunction with the powder recoating system, we also have some, say, good practices or guidelines for achieving the best build quality and avoiding defects. And some such cases are illustrated here. The incorrect or non-optimum orientations are shown in red, whereas the optimum orientations are shown in green. And here, the consideration is that we are trying to minimize, say, the number of edges which are parallel to the recoater. If this is the recoater axis, in the red configuration, we see that it is also parallel to the recoater. And what happens then is that a very long section is in contact with the recoater at all times. So, say if there is some warpage in a local region, or somewhere locally the powder layer is depleted and the part comes in contact with the recoater, then it can lead to propagation of error and damage of the machine. Whereas if we just tilt it by a small angle, we are seeing that now for each pass we have minimized or brought down the length of the part which is in contact with the recoater blade, effectively preventing such an occurrence. In the other case also, where we are printing multiple parts, instead of aligning them together very neatly, we should stagger them, again slightly tilting them from the recoater axis based on the principles we just discussed, but also spreading them out to prevent a propagation of errors. Because if for some reason the recoater or locally there is some damage or some error, then it will get propagated over the powder layer and can affect also other neighboring parts. Also, staggering them like this gives us proper machining allowance to, say, later remove each of these parts individually by a typical process like wire radium. In terms of the build atmosphere that is used for printing parts using selective laser sintering and selective laser melting, we may either work with an inert atmosphere, typically using gases such as argon and nitrogen. Of course, to ensure that the oxygen concentration inside the chamber is well below the control level, such as say 100 ppm or lower, to prevent contamination of the chamber and of the powder particles, because powders, as we know, have a much higher specific surface area or surface area per unit volume compared to other feedstock types such as sheet or wire. Also, depending on the type of inert gas used or the composition of the inert gas, in case we are using a mixture, uh, the properties of the final build part have been shown to change. Or we may be printing in a vacuum, which becomes an essential requirement for the case of electron beam based selective laser sintering or selective laser melting machines. Of course, just to recall, the reason being that the principle by which an electron beam transfers energy to the pre-deposited layer or substrate is through the transfer of kinetic energy. Electrons themselves are very light particles, one of the lightest of the subatomic particles, uh, and so they can be accelerated to very high speeds. They can transfer this kinetic energy to the target material. However, being so light, if in their path they encounter a heavier molecule or some other obstruction, they can very easily get uh, deflected and dispersed. And so it is essential to ensure that the path of the electron beam is clear, and this is ensured by having a vacuum. Or for processes such as binder jetting, the atmosphere may just be kept open, because in the case of typically binder jetting, there is no say fear or threat of oxidation. It is a room temperature process, and so the machine on the powders may simply be kept open to atmosphere. Of course, we're not having atmospheric control, but there will still be some say controls in place to ensure that the powder particles do not disperse into the atmosphere or not breathed by any human operators. Now, the classification based on subsystems of the joining mechanism, the powder material, scanning system, powder delivery system, powder recoating system, and build atmosphere, and their combination can lead to different types of technologies and machines, such as if the joining mechanism is sintering, the powder material is polymer or wax, the scanning system is a galvanometer, the powder delivery is by bottom feeding, and the powder recoating system is a roller, and the build atmosphere is open. Or if the joining mechanism is sintering, the powder material is polymer or wax, the scanning system is a galvanometer, powder delivery is still from the bottom, powder recoating happens by a blade, and the build atmosphere is open. Or another machine where the joining mechanism is sintering, the powder material is coated, scanning system is galvanometer, the powder delivery system happens by bottom feeding, powder recoating system consists of a doctor's blade, and the build atmosphere is open. Uh, we have an example of such a machine here. Or we may also have a case of liquid phase sintering, where the powder material is mixed, scanning system is galvanometer, powder delivery again by bottom feeding, powder recoating is by a roller, and the build atmosphere is still kept open. Or we are using the principle of liquid phase sintering for a pre-alloyed powder material using galvanometer as a scanning system, powder delivery from the bottom using a roller for recoating, and an open atmosphere. Now, just like the other AM processes that we discussed, a generalized flow will consist of pre-processing, build process, and post-process steps. Pre-processing includes making the digital design or obtaining it directly, then tessellating it or slicing it either directly or indirectly, checking for vulnerable regions such as overhangs, generating support structures if needed, and transferring them to the machine. Also, say loading of powder, uh, loading and clamping of the build plate, cleaning of the machine, changing of process parameters, or say in the case of order bit fusion, even there might be multiple laser spot sizes available, then choosing the specific parameter space. Then there is the building process itself, which consists of the actual building process where for each layer the powder is brought from the reservoir and passed on to the printing region by the recoater. It's spread into a thin layer of uniform thickness as specified or desired, and then scanned by the laser, and then many hundreds or thousands of such steps. And finally, post processing, which will consist of, say, removal of the support structures, if any, such as shown here, uh, separation from the build plate, and also something like hot isostatic processing, hot isostatic pressing or HIP to improve the part density. Some hybrid systems have also been designed, uh, such as shown here, which have a combination of milling, squeezing, and sintering. So there are some pre-existing sintered and milled layers uh, over which a squeezing blade passes and introduces new powder into the system. Uh, this powder is then compacted and spread out into a thin layer and then sintered using a laser. 10 such layers are squeezed and printed, and then a high-speed face milling or end milling step ensures geometric accuracy to produce parts of enviable tolerance. And some such technologies are shown here, such as a Lumex 3D printer by Matsura, Sodic metal 3D printer, and the machine by Boyle lasers. And the present slide also has example of parts built by laser powder bed fusion. And often the parts may have such good surface finish that it sometimes becomes difficult to recognize that they were printed in the as is condition and not machined with some post processing step. And that brings us to the end of the course contents for this week. So we'll just break for a short while, and when we return, we'll be looking at example problems that will help reinforce these concepts and will be useful for solving the assignment problems for this week. Good evening, and welcome back to the live sessions. So we'll now be looking at a few example problems related to the course contents for this week. The first question is asking us, what is the role of support structures in laser beam based additive manufacturing uh, process? Is it A, to support the overhanging features, B, to prevent warpage of the parts, and C, to take heat away from the deposited layer, or is it all of the above? So we'll remember this familiar picture from our discussion where the entire bed was, we had this part, and the bed was also filled with unsintered or unmelted powder particles surrounding it, and then there were these support structures connected to it. So is it to support the overhanging features? Of course, because that is the default or one of the most important or primary roles of support structure. So A is definitely true. Is it to prevent warpage of the parts? We discussed how uh, in a powder bed process, we will have a recoater blade or a roller, which will move over or traverse over the printing region in any path to deliver the next layer of powders and spread it out in a uniform fashion. Now, because of the high thermal gradients and very high cooling rates, uh, there's a good chance that the part can distort and warp. And if it warps, say it may move up compared to its original position. And then there's a good chance that it can collide with this moving recoater blade, which will damage the blade and the machine. It will damage the part and it will stop the printing process and send the machine into downtime. So we want to prevent any such occurrence because the tolerances here are really small. As I said, this layer thickness will only be few tens of microns thick, and so even a small amount of distortion or warpage can lead to damaging the recoater blade. Is it to take heat away from the deposited layer? Now, as we discussed during our last session on numerical modeling of the additive manufacturing process, there are certain avenues for heat loss from the system. It is by convection. So something like some heat transfer coefficient times the actual temperature minus the free stream temperature, and also by radiation, where it is Stefan Boltzmann constant times the emissivity into actual temperature to the power 4 minus the ambient or the radiation temperature to the power 4. And then there is heat conduction away from the part by the substrate. Typically, it is not counted as a loss, but rather the loss is mostly accounted from the convection radiation. Now, let us consider a process like electron beam melting, which is also a powder bed based process. In electron beam melting, because of the presence of only vacuum, this convection heat loss or convection heat transfer is minimized significantly. And so, the heat transfer away from the part is not as effective or not, say, as significant as in the other cases where we will have, say, a stream of argon gas flowing over the part. And in such processes, especially, uh, the support structures will have this additional very important function of taking away heat from the deposited layer. And so what we can see is that all of the above are the roles of support structures in laser beam based powder bed additive manufacturing process. The second question is asking us, what is the advantage of using a roller instead of a blade as a recoating system in laser beam based powder bed additive manufacturing? So if you will recollect, we had both of these recoater types. One was just a blade, head of which we had powder, which it would then spread over the printing region. And we also had roller. In roller, we saw that depending on the relative motion between the traverse direction and its rotation, we can have a forward rotation or a counter rotation configuration. And again, its job was pretty similar to spread out this uh, available powder into a fresh layer. The advantage of using a ruler instead of a blade arises, as we discussed, from the difference in degrees of freedom. The doctor's blade has a single degree of freedom associated with linear translation, whereas doctor's blade will have 2 degrees of freedom. The ruler will have 2 degrees of freedom associated with the translation as well as with its angular rotation. Does roller lead to more uniform distribution of powders? This is correct. We saw that how uh, while doctor's blade is capable of handling a larger quantity of powder per layer, the distribution may not be as uniform and the packing density may not be as good as that achieved from roller. Further, depending on the configuration, whether it is a forward rotation or a counter rotation type setup that we are using, they will also have individual advantages, such as a counter rotation setup improves the flowability of the powder particles, whereas a forward rotation improves the compaction of the powder bed and the packing density of the powder bed. And so it does result in better compaction of powder layers and greater packing density of the powder bed. Of course, it has advantages, and so here we have A, B, and C as the correct options. The third question is asking us, which material is preferable for making the blade of the recoating system in laser beam based powder bed additive manufacturing? Is it silicon, as it can lower the cost of the machine? Is it metals or alloys, because of their ductility? Is it ceramics, as they offer good geometric tolerance? Or is it polymers, as they are typically lightweight? Uh, we should recall and consider uh, the physical conditions which the recoater blade is subjected to during powder bed based printing. to be able to answer this question. So if it is a sintering process, it will be subjected to high temperatures in the range of half of melting point to up to melting point. If it is a melting process, then the temperatures will exceed even the melting point. Say for steel, the melting point will be around 1723 Kelvin, 1400 odd degrees Celsius. So that is the order of the temperature which it will be subjected to. Then it needs to ensure good geometric tolerance because the resolution will depend on the layer height. So the layer should be very uniform and well spread and compact. If we use silicon, it may melt easily, and further, we did not really encounter any evidence which would suggest that the use of silicon will necessarily lower the cost of the machine. Typically, these costs will arise from other factors, and the cost of the blade will uh, not really be the largest contributor. Metals are ductile, but then because of the high temperatures of say the immediately printed part or the heat which is still available in the layer, it can easily lead to distortion of these metals, affecting their shape and the geometric tolerance. And ductility is not really a quality we are looking for here, so this is unlikely. Ceramics, because they offer good tolerance, is of course very important because this good tolerance and tight control will enable us to have very well controlled and layers of desired thickness. Further, they handle thermal shock very well, far better than metals. So ceramics are a good choice. And polymers, even though they are lightweight, will typically end up melting under the temperature and extreme conditions which are encountered inside the powder bed fusion machine. So ceramics is the correct answer. Now during the session, we saw at least a couple of examples outlining some good practices or the correct guidelines for orientation of parts in the bed of a laser powder bed fusion machine. So we'll just do a few exemplary exercises which will help us to understand and apply these principles. And so I have a few questions where we have a part in its default orientation, and we'll try to orient it optimally based on the prescribed guidelines. So for each question, I'll maybe wait for a minute to allow the audience to attempt it or understand the configuration, and then we'll discuss the solution. So please take a minute to uh, say understand and observe the current orientation of this part and how it can be improved or what are the guidelines uh, which should be considered uh, while optimizing this orientation. And if you are watching this video at a later time, you can pause here and then proceed to the solutions. I'll just wait for a minute. One of the principles which we discussed during the session was that we should try to minimize the number of edges which are aligned exactly with the decoder blade. And the purpose for this was to reduce the say the surface area of the part in contact with the recoater plate at any given time. Here, the recoater axis and the part axis are parallel, and so this is of course not optimal. Further, we can see that in every pass, uh, say almost the entire cross section of the part is in contact with the recoater blade. So some of the guidelines guiding this can be that minimize the number of surfaces or edges or lines parallel to the recorder. Second, to minimize the contact length of the part with the recording system at any instant. And in this case, we see that both of these guidelines can be achieved by just uh, say reorienting it by 90 degrees such that now say the thinnest uh, section of the part is now in contact with the recorder plate at any given time. And so what we are seeing that at any given time only the small area of the part will be in contact. And I also have the optimal solution here. So at the bottom we have the support structure to allow for machining allowance while separating this part from the build plate. And then we have reoriented it such that we minimize the number of edges which is parallel to the recorder blade, and this is the total length of the edges which are parallel now. And also we minimize the surface area of the part which is in contact with the recorder at any given time. This is the second question, which might be similar to what we saw in the slides, and so it should be easier to attempt. Here already each individual part is say twisted or tilted with respect to the recorder axis in order to minimize the number of edges parallel to it, but they are still say available or spread out in the part in the bed. So let us see if there is any further optimization or reorientation or readjustment which can make this print better. So please take a minute to consider what other changes can be performed here, and maybe you can get some hint from these parallel lines which are parallel to the recorder axis. Here, the relevant guidelines can be to minimize the propagation of defects, minimize the contact length of the part with the recoating system, just like the previous case, and to minimize the number of edges parallel to the recorder. Now 3 is already taken care of by twisting each of these such that now their edges are no longer aligned with this recorder axis as is already shown, but all of them are still aligned with each other along this parallel axis as shown. And so one additional step which we can be done is that we can offset these parts by some variable distance. Like the bottom one can be kept as is, the middle one can be shifted by a small distance, and the top one can be shifted by significantly larger distance, such as to offset them effectively. Once they're offset, of course, we'll also have say sufficient machining allowance to separate them from the printing region, and we will be able to minimize the propagation of any defects which may erupt in between. And the correct solution is also shown here. Of course, it is important to point out that this is just one of the optimum orientations. It may vary depending on the use case because say for our individual prints, we may be trying to achieve different objectives. One may be trying to print in the shortest amount of time or with the minimum amount of powder, or they may be targeting for strength. And so the optimum orientation or distribution of parts inside the print bed may change, but these are just some general guidelines which will be mostly suitable for in an overall sense. So here again we have a part, this time with a cylindrical through hole. So let's assume that this is a through hole, and some support structure already shown in this present case. And so let us try to think of a better orientation, uh, which will be an improvement over the current scenario. Here we are seeing that there are support structures subtended on the internal surfaces. And what we can try to do is maybe minimize the support structures and try to improve the surface finish, especially on those internal surfaces. And to achieve this, in this case, the guidelines can be to minimize the support structures and to minimize the support structures um, subtended on the part surfaces itself. Of course, the intent to minimize the post-processing effort. And here, one very easy way or direct way to do that is to just tilt it by 90 degrees so that this through hole comes on top. And since it's a through hole, now we have totally gotten rid of support structures, not only inside the circular hole, but also at the bottom where previously the entire bottom face needed to have support structures, but now we have also gotten rid of the support structures over this whole region. And so we have achieved both of these objectives, being to minimize the number of support structures or the volume of support structures, and to ensure proper surface finish on this inside whole feature. Of course, it is already oriented such that the number of edges parallel to the recoater blade or the length in contact to the recoater blade per unit time is at a minimum. The standard solution is also shown in this present slide. And this is of a similar kind. Okay, this one appears interesting. So I also have a couple of more examples which the participants can solve on their own. I have also attached the standard solution for them to compare. And this is somewhat different. And so let us try to do this and take a minute to come up with the optimum or better orientation for the part shown here. In this case, it is already the part is already oriented in a fashion such that none of the edges are parallel to the recoater axis, as well as uh, the inner plane, the line or the length uh, in contact with the recoater blade, but at any given time instant has been decreased or minimized. However, and this is almost identical to one of the example cases that we saw in the slides. So what different can we do? What we can see is that in a plane, the amount of or in each pass, we are printing the same surface area of the part. That is, it is arranged. If we look at, say, some side view, if this is our print bed, we are printing prismatic section in each layer. Say, if I just were to blow this up and say divide it into 4 layers for the total part, we are printing the same cross section area in each pass, almost in a prismatic fashion. So what we can do is instead we can raise one end, or uh, if we look at a 2D view, we can tilt it like this. And by doing this, now what we have done is in each layer, because the slicing will still be planar, we are now printing differential surface areas rather than printing prismatic cross sections. And so in each pass, only a very small area or cross-sectional area of the part will be in contact with the recoater blade. And so this may be one of the ways to improve the orientation of the part. As I said, we have a couple of more questions which the participants can take up and try to solve. The standard solutions are already provided. And with this, we come to the end of this live session for the NPTEL course on fundamentals of additive manufacturing technologies. This is the penultimate week of the live sessions, and we'll be having the final session next week on Tuesday. With that, we would have spent 12 weeks uh, exploring this very fascinating and disruptive technology of additive manufacturing. And I thank you for tuning in to this week's live session. And I hope to see you again in the next week. Thank you very much.